Welcome. In this particular talk we're going to have a look at the game loop. This is the central mechanism within our games that sequences the updates and the draws. And we want to have a look at how we can manage this process so that we get a consistent number of updates per second. So we'll start off having a look at the basic game loop, and then we'll go on to look at some more sophisticated forms of looping. Why do we need a game loop? First of all, we didn't always have them. In fact, some of the first games simply ran as fast as they possibly could. They did an update of the world, then they drew the world. They did an update of the world, and then they drew the world. And they just kept on doing that. It was a rather different world back then. Certainly processors were nowhere near as fast as they are nowadays. And there's also a much greater degree of homogeneity across them, that if you were running on a Commodore 64 or an Acorn or whatever, that the processor was of a fixed speed. So one person's computer was as fast as another person's computer. It worked then, doesn't work today, where you have faster machines or you have a greater degree of variability in terms of the overall capabilities and speed of machines. So it means that we need to have some way of managing this process. The first early attempts, as you can see the diagram here, is that you check to see, as the user provided in the input, you update your game and you draw the game. And then you maybe wait a bit and you repeat this particular process and you iterate around that. So you have a fixed frame rate, and every once in a while you get a tick, so you set up a timer. That timer then triggers the process, update and render. It seems perfectly sensible. In terms of why it can be problematic, one of the reasons is that the update and the render are effectively tied together. So that if you're entered into a particular busy period of the game, where you're maybe aiming for, say 50 updates and draws a second, but you're drawing something that is particularly graphically intense, it could result in your number of updates per second being reduced as well. So the two things are coupled. And this is problematic because if I'm having to reduce the number of updates that I draw per second, then it's not necessarily only that I'm drawing it slower to the screen, but that the game itself is updating at a slower pace as well. And that can be problematic if I've assumed a particular fixed number of updates per second. In that case, my game will actually run slower, not only be displayed slower. So we want to avoid that particular issue. How do we avoid it? Well, you have an opportunity to try to solve this yourself. So here we have a problem. I want to assume that you have a number of methods, and all the methods you need are simply here. We've got one method called update, which will update all of our game objects. We've got another method called render, which will draw all of our game objects, or draw the bit of the world that's visible. We have a method called time, which will return the current time. And you can assume here that it is a time that is accurate to the nearest millisecond. And we also have a method sleep, which will, we're assuming an individual thread here, we'll put this thread to sleep for a specified number of milliseconds. And given those four different methods, I want you to have a think and spend 10-15 minutes developing an algorithm where if I give you a target number of updates per second, that you will try to hit that target number of updates per second. And you'll do so in a way that, if need be, you will skip renders. So if I'm getting behind myself, then we'll just avoid drawing that particular frame. We'll lower the number of frames per second, but we will try to hit our number of updates per second. So hopefully 10-15 minutes, maybe that's all it should take, but do pause this and take an opportunity to go over your particular algorithm for doing this. And we'll have a look at a solution in a couple of slides' time. In terms of the solution that we have on the next slide, there's one little caveat that we need to put into it. And this comes into the sleep request, where we may be asking to go to sleep for, say, 3 or 4 milliseconds. If we're aiming for, for sake of argument, say 50 frames or 50 updates per second, that means each update we're anticipating we can fit into 20 millisecond periods. And if we do an update and a draw and it takes a total of 17 milliseconds, for example, then we want to wait for 3 milliseconds. That's the time the next update would be due at. So we could go to our sleep method and request that it sends us to sleep for 3 milliseconds. Sounds perfectly reasonable. However, certainly on current hardware, if you ask to go to sleep for 3 milliseconds, it may not be accurate to the nearest millisecond. You might be woken up a millisecond early. You may sleep in for a couple of milliseconds. So there is a degree of inaccuracy overall in this. And this is problematic because over frames, these errors can accumulate and can add up, and your game can ever so slowly get out of sync over a longer play period. And we want to avoid that. So we'll try to take into account the fact that our sleep requests may be inaccurate. And here we have the particular algorithm that will enable us to try to hit our target number of updates per second. It looks complex. It's not actually that complex, and the whole thing fits within 20 lines of sort of pseudocode here. So we'll go through it. A few variables are defined at the top in the yellow box. We have one for our update period. This is the number of milliseconds that we are trying to target for each of our updates. So there you can see it's just 1,000 number of milliseconds in a second divided by the number of updates per second. We have time beyond period. Initially it's set to 0, and this is the thing that we will measure how far behind our target that we're getting. So if we're running 5 milliseconds too slow, we're 5 milliseconds behind where we want to be, then this will have a value of 5. And over time is going to be a value that a positive value here will indicate that we have slept in. We wanted to go to sleep for 5 milliseconds. We actually went to sleep for 7 milliseconds. So we'll wake up, and this will have a value then of 2, for example, that we slept in for 2 milliseconds. Okay, so given those variables, let's have a look at the actual algorithm itself. So we've got a while at the top, and while we're running, we'll keep doing this. So while the games keep going, we want to update and we want to draw. We record the time at the very start. Then we do an update and we do a draw. So we update our world and we draw it out. And then we measure the time at line 5 after that has happened. So once we've measured those 2 times, we'll know how long did it take to update and to draw. Line 7, we're working out how long do we want to go to sleep for. So here we're looking at update periods. So for example, say it's 20 milliseconds is our target. We're taking away from that t after minus t before, and that effectively is how long did it take to do our update and our render. So if it took 17 milliseconds, then it'd be 20 minus 17, that's 3. And the final bit at the end is we're taking into account, okay, on the previous frame, we could have gone to sleep. Now, did we wake up too early? Did we wake up later? Let's take that into account. So, sake of argument, if it was 20 millisecond target, it took 17 milliseconds for our update and render to happen. And in the last frame, we slept in for an additional 2 milliseconds. Then our overall sleep time here would be 20 minus 17 minus 2, or 1. Important little caveat on this. If we're going to sleep, yes, we could sleep in too long, and that would give a positive value in over time. If we get woken up too early, so we wanted to go to sleep for 7 milliseconds and we got woken up after 5, then over time we'll have a negative value. We'll have a negative value here of minus 2. So a negative overtime value represents the case where we got woke up too early. And if you think about line 7, a negative value in the previous frame will actually increase the sleep time on this particular frame. So we constantly, each frame, try to take into account any inaccuracies in it. So after line 7, we know how long we want to go to sleep for. So line 9, we check to see, is this a positive value? In other words, is it something we actually should go to sleep on? If it is, line 10, we go to sleep for the value we've calculated. And at line 11, we're working out, okay, we're assuming that the sleep request blocks until we're woken up. At line 11 we say, well, what's the current time? And we take this away from time after minus time asleep, which is how long we thought we were going to go to sleep for. And that gives us our overtime. So in other words, here we have the error in the sleep for that particular request. So positive value, we slept in. Negative value, we woke up too early. At line 13 we have our else. Now this is the else to the if, and it will trigger if sleep time is negative or 0, but negative is the particular thing we're interested in. So at line 13 else, we don't need to go to sleep. And if we don't need to go to sleep, it means that we are actually struggling to keep up with our target. We don't have any spare time. So what we do in line 14 is we say, okay, we are running slow. Let's work out how much we are running slow. So time beyond period is equal to time beyond period. Take away the sleep time. We need to think about this here. So a positive sleep time means that we need to go to sleep. A negative sleep time means that we don't want to go to sleep. In fact, we're actually running slow. So if we time beyond period and we take away a negative value, we effectively add it on. So line 14 works out for this particular frame how much are we behind our particular target, and it's an accumulated figure. On one frame maybe we're only 2 milliseconds behind, the next frame we're a little bit extra, we're now up to 5 milliseconds behind, the frame after that could be a bit more, we're now 10 milliseconds behind. So it's something that if we're having a challenging period within the game, we can accumulate. Line 15 says overtime is equal to 0. So if we're behind with ourselves, doesn't matter about the overtime, let's just set it to 0. We just want to get caught up. Line 16 is the important one. This says that whilst the time beyond period is greater than the update period. So in other words, if we get sufficiently far behind ourselves, so we're lagging behind, that it reaches the period that we normally would want to do an update within. So if we're 20 seconds is our target update period, and we're actually now 20 seconds delayed, or sorry, 20 milliseconds, then we should do something about that. And what we do about it is in line 17 and 18. So we trigger an update, but we don't trigger a draw. So this is our way of saying that we really are expecting an update to have happened now. Let's do an update. Let's not bother drawing it because this will hopefully save a bit of time. In line 18, we then correct the time beyond period. We say, okay, let's step forward to the next update. And if need be, we will repeat that while until we've notionally got caught up with ourselves. To get caught up, it assumes that our update always effectively can complete within the update period. If it actually is our update that is taking longer than the update period, irrespective of the draw, then we're in a position where we can never recover from. But if it's the draw that is the thing that's taking us behind it, then yes, arguably we can get caught up with ourselves. So a fair amount to this, but in essence, it is just those same number of simple steps about measuring, looking, going to sleep, and correcting if need be. By way of some more advanced forms of looping, we'll have a look at some usual or potential extensions to the previous couple of slides. One of them is to break away from the notion that updates occur at a regular interval, and almost to embrace the fact that, well, okay, an update could occur every once in a while. It's not going to be a regular interval. And this is where variable steps come in. So here we update and we draw as fast as we possibly can. There's no waiting. We update, we draw. We update, we draw. The thing it changes is that as part of the update and as part of the draw request, we pass in how much time has elapsed since the last update or the last draw. So they are conditional on the particular delta step that's coming into it. If you're running on a faster machine, then you'll have more updates and more draws, and the delta value will be smaller. If you're running on a slower machine, then you'll have fewer updates and draws, and the delta value will be bigger. And it means you need to write your update and your draw method so that they take into account the actual time step that is elapsed. They don't assume that it is a fixed period of time. So it makes the update and the draw a little bit more complex, but it does mean you don't need to worry then about what happens if you do get behind, because it'll automatically correct. The final thing I want to pull up here is, we're only in the briefest possible way touching upon it in this slide, but this is incredibly important. Machines nowadays, tablets, consoles, PCs, they are all multi-core, and number of cores are increasing. Basically, all of these devices also have specialized GPUs. So you have two chunks of silicon, a CPU and a GPU, and even within those chunks of silicon, you have a number of separate cores within it. So parallelism is vitally important, and if we only ever write our game with one thread of execution, we are in most cases underutilizing, often considerably so, the capability of the hardware in which we're running. So ideally we want to design our game loop and our game engine to exploit the threads that are available. There's lots of different ways of doing this, lots of quite interesting things you can look at here. We're not going to touch upon it at this particular point within the module, but I'll flag up one possibility that's quite nice, I suppose. And you can see it down at the bottom, where we want to avoid a situation where we update our world, where we have our CPU being busy, and we then draw our world where we have our GPU being busy. And it's not a great situation where when the CPU is busy, the GPU is idling, and where the GPU is busy, the CPU is idling. So we want to sort of use both these chunks of silicon at the same time. One way of doing that is that we do a couple of phases in concurrent processes. So we render the world at time t. You can see this down in the diagram. So we're drawing the world and what it looks like at time t, or step t. Alongside that, so that the rendering of the world keeps the GPU busy. Alongside that, we keep the CPU busy by planning how we will update the world at time t+1. So we're not updating it yet, we're just planning. We may be looking for any collisions that are coming up. We may be running our AI routines to work out how our game objects want to change at the next time interval. And that keeps the CPU busy. And if you had a multi-core CPU, again, you can farm out these different things across the cores that are available. After that, you then have your update world to time t-1. And that is the thing, you have only one phase. It gets the objects actually to put into action whatever they have planned, and you then iterate around. So then we're drawing the world at time t-1, and we're preparing the world at time t-2. And it's a nice way of really sort of moving away from the update draw to an update and a concurrent draw and plan phase, and that helps by way of overall efficiency. One key thing for you to remember whenever you're designing your game objects, and this is a good thing to enforce, is to make sure that you do decouple the update and the render behavior. So always ask two separate objects of each of your game objects, or two separate questions rather. How will I update this object? Answer that, put that answer if you like within the update method. And how will I draw this object? And put that aspect within the draw method. So for example, if you had an animation, the frame of the animation that you want to use at a particular time and point in time, you would decide that within the update, and actually when you're drawing it, you then draw that particular frame of animation. So do keep those two phases distinct. But at the bottom, the draw phase should not change the game state. That's quite important that you enforce that. It means that, for example, if you want to pause the game, you simply stop updating it, but you can still keep on drawing it, and you're basically drawing the game frozen at a point in time. And because you haven't polluted the two in terms of how things get to be evolved, the game will properly pause. So there's lots of advantages that arise from doing this. So key takeaways, I have 3 of them for this one. Getting a smooth number of updates per second can be a bit fiddly, but it's not that difficult overall. To be fully effective, the game loop needs to be designed to support multi-threading. You can, if you wish to, in terms of the engines you're developing. You may want to push that back to one of the later sprints and get it up and running first of all in a sort of a nice single-threaded way. It is the type of thing that you can reasonably easily introduce into it, but depending on the type of concurrency or multi-threading you are putting in, there can be significant revision needed to the code. Just depends. And the final one, always remember when you're looking at your game objects, do consciously decouple the update and the draw behaviors. That will help you quite considerably.